what we were doing in the last class. So we were actually dealing with Ising model. So what is the model? The model was one dimensional, like you have n number of sites on 1D, and each site you have a spin sitting there. The spin uh, could be in two states, either spin up or spin down. This is like a spin half particle, and there is interaction between the nearest neighbor. So if I take ith spin, then it interacts with I plus 1 and I minus 1. So in addition, you have an external magnetic field. So you can actually write down the Hamiltonian. The Hamiltonian looks something like this. The first term is the interaction between the spins, nearest neighbor interaction, sigma I and sigma I plus 1. Then you have external magnetic field B. So, this part of the Hamiltonian is due to the external magnetic field interacting with your system, your each magnet, and then the J sitting there, which is the strength of the interaction. I put a minus sign there, and the convention is that you take J to be 0. Essentially, which basically means that if both the spins are up or both the spins are down, this energy is minimum, so that is preferred, and this is called the ferromagnetic state. A true ferromagnetic state would be one where all the spins are up or all the spins are down. Okay, this is a true ferromagnetic state. Okay, and now you have to calculate the partition function. The partition function would be given by this, which is essentially exponential of minus beta times this Hamiltonian, and you sum over all spin states. So you have n number of spin, and each spin can be in two states, spin up or spin down. So these are spin variables, sigma 1, sigma 2, sigma 3, sigma 4, up to sigma n. Each of these could be in plus 1 or minus 1 state, up or down state. So now, in order to calculate this partition function analytically, we just make use of what is known as periodic boundary condition. We say, okay, my sigma 1, the sigma n plus 1 1th spin is actually your first spin. So I just make a loop, make a ring shown here. So this is sigma n minus 1 1th spin, sigma nth spin, and this is sigma n plus 1th spin, which is equal to the first spin. So this is what is known as periodic boundary condition. Okay, once we put the periodic boundary condition, you can actually write down the partition function like this. You can put sigma I plus 1. So you had sigma I here, and you can see that here you put sigma I plus 1 divided by 2, and this is your partition function. And then I said, okay, this partition function, since this is an exponential, and then in the exponent of the exponential, this you can write as a product of exponential, and on top of that you have sum over all spin states. Okay, so this quantity I'm calling it m sigma I plus 1. These are matrix elements. This is a matrix element we'll show later for a 2x2 matrix, which has elements like both spin ups, both spin down, one up, one down, one up, like this. So essentially, partition function is a sum over all such matrix elements. Okay, and this matrix has a name. This matrix is called transfer matrix. Okay. Maybe I have not mentioned it here, but I can mention it. This matrix is called transfer matrix. I hope everybody is following. If anyone is having problem, tell me. So this is it's called transfer matrix. I hope everybody is following. Anyone having problem? Yeah, should not be, because it is just a repetition of last class. Okay.
Yes, sir.
I'm
Fine.
just repeating this because recalling you what I did in the last class is important. Okay. Yeah. So your partition function is product of such matrix elements, and then you have to sum over all the spin states, sigma 1, sigma 2, sigma 3 up to sigma n. And then what I did, I said, okay, since okay, okay, So this is your matrix M 2 cross 2. So then what I did, we said that, okay, actually this matrix element, if you look very carefully, what is this matrix element? This is shown here. And this I showed that, okay, actually you can express, this should be somewhere here. Have I written this? Or let me check. Should be somewhere. I must have written this. Yeah, here. Your matrix element is your sigma I plus 1 is actually this sigma I plus 1. So these are the basis. And M is your operator like this, isn't it? What you do in quantum mechanics. It's the same mathematical technique. And you also make use of this resolution of identity. You actually insert this in between. You don't need to insert actually. If you expand this, you'll see that they're sitting there, sigma 2, sigma 2, sigma 3, like this. And you have the sum over sigma 2, sum over sigma 3, all this. So each of them you can collect, each of them will give you identity matrix, 1. And then this M will be placed next to each other, M, then M, which becomes M square, then M cube, then M to the power of 4. And there are n number of such n. So you'll have M to the power of n sandwiched between two matrices, sigma 1 and sigma 2. Yeah, two bases, sigma 1 and sigma 2. And sum over sigma 1. And this is nothing but the sum of the diagonal element. This is called trace of M to the power of n, shown here. And as I told you that M has 4 elements, you can work it out. And if you explain, say, if you use beta j equals to x, beta b equals to y, then it has the structure like this: exponential of x plus y, exponential of x minus y, exponential of minus x, exponential minus x, shown here. Okay. And you can also check that M dagger equal to M. So this is Hermitian matrix, so it should have real eigenvalues. And you did a little bit of matrix algebra, and you show that the trace of a to the power of n, if you have trace of a matrix A is a sum of diagonal element, then trace of a square is sum of the square of diagonal element, and trace of a to the power of n is the sum of the nth power of the diagonal elements. Okay, so you make use of that. So essentially it tells you that your trace of m to the power of n is going to be sum of, because M is a 2 cross 2 matrix, there will be two eigenvalues, lambda 1 and lambda 2. So it will be equal to lambda 1 to the power of n plus lambda 2 to the power of n. It's shown here. I called it lambda plus and lambda minus. Okay, this is exactly what I did in the last class. So then we solve this 2 cross 2 matrix, little bit of algebra. And after doing this little bit of algebra, putting these values, you see that lambda plus minus is given by this. You know what is x, what is y. I think that in the next page we showed that actually this lambda plus in the limit, which is called thermodynamic limit, n goes to infinity, you have a large number of spin states, then this lambda plus is much greater than lambda minus, so it will dominate. And so you can approximate this partition function only with one of the eigenvalues, the largest eigenvalue, which is lambda 1 or lambda plus rather, 4 to the power of n. And this is your partition function expression. And then if you take a log of this and multiply this minus kBt, you will get Helmholtz free energy. So this is Helmholtz free energy. It scales with the number of particles n, shown here. And then we had started working out other thermodynamic quantities. And in this case, very important thermodynamic quantity in this model is what is known as average or mean magnetization, which is shown here, M, capital M. And I said this not the matrix M here. This is magnetization. So this is clear that this M and this M, they are different. Is this clear?
Yes, sir.
Should not. I have written clearly. Not matrix M. Here magnetization. Okay. So and what is magnetization? Actually, a magnetic moment times the spin state plus 1 or minus 1. You add the spin state on each side and add them, like side number 1 up, side number 2 maybe down, add, then up, then down. You can have many configurations like this. If you add them and then average over all such configurations, it will give me average magnetization. Is this clear? This is ensemble average. Is this clear? That one realization would be like n number of spin arranged in some fashion, up, down, down, up, down, down, up, down, like this. Next arrangement, you flip one of the spins. Next one, you can flip two of the spins. And there are many such arrangements possible. So this average is over all such arrangements. It's like ensemble average. And this is equal to, if you do carefully, I am not doing it again because you can do it yourself. It is equal to n times mu and the partition function is now given by lambda 1 plus to the power of n, so that's why n comes here, and you take a derivative of this lambda plus with respect to y. You remember what is y? Y, what is y? Y was beta times b, because b means mu times h. Check your notes. Magnetic moments times the magnetic field is the strength of the magnetic field, which is b, capital B. Okay, that is y. B times beta is y. You check your thing, and then I have to calculate this magnetization. Of course, how do you calculate? You actually take the expression for lambda plus, and you differentiate this with respect to y. And I stopped here. I stopped here. Okay. Any question? We'll start from here, today's class. I hope there is no question. I'm just hoping. Okay. So let us start here. Can you see clearly? I hope you can see clearly. Okay. So this is your lambda plus. So if I take a derivative of that with respect to y, you know, this ln of some function of y, 1 over that, and then this function has to, one has to take what is that called, derivative of this function. Is this clear? And this is exactly what I did. No, ln of this is 1 over this. The first time will give you cos hyperbolic y will become, because del y of similarly. So exactly what I did is this, and what will happen to this? This is like root over. Root over means half nx to the power n minus 1. No, half 1 over root over this, and then you have to take the derivative of this argument. Okay, so this sine hyperbolic square become 2 sine hyperbolic y times cos hyperbolic y. Okay, is this clear what I have done so far?
Yes, sir.
So let us see what. So let me write down your average magnetization now becomes sine hyperbolic y into this comes because of this. Of course, you have this in the denominator, you have, which I can put it here. And you already had this. I hope this is fine with you, the one I have written here. Okay. Any problem so far? Should not be. If you have any problem, please let me know. Huh?
Fine, sir.
Fine, no? So let us go and paste it here. Yeah. So this is your expression for this. And then what you can do, you can just say, okay, your m t comma t is your n mu. Here you can see you can take exponential of sine hyperbolic y common, isn't it? So I take exponential of x sine hyperbolic y common. What I have here, I have this. What I'll have here,
X was hyperbolic y.
yeah. And in the denominator, what I had sorry for this handwriting, huh? This is the problem, not writing on blackboard. So can I simplify this further?
Yes, sir.
What can I do? Just look at
Moment.
it. This one and this one, they're same, no?
Yes.
Then what I have here? I have here is n mu exponential of x. This one I can further simplify. I take exponential of 2x common from the root. So outside it will become x. This is fine, the way I've written. Is this fine the way I've written it? Should be fine, no?
Yes, sir.
I hope you're following. It's not very difficult. And what I have here now. So what I have here is n mu. Now what is sine hyperbolic? What is y? Anybody remembers what is y?
Beta B.
Beta B.
And what was x?
Beta J.
So this is your expression for the average magnetization. Is this clear? And I can also define, so for example, I can define uh, average. This is average magnetization. And I can define something like Sorry, sorry for this. Be very careful while doing this. What is this? If I write like this is called average magnetization per spin. Is this fine?
Yes, sir.
Okay. So now look at carefully what happens to this expression. The expression is this, no? Shown here. Now, uh, uh, think of a situation that there is no external magnetic field. What will happen?
Is equal to 0.
Let me see. It basically means B 0. Then what will happen to this average magnetization, say this one, or you can divide by n. What will happen to this?
0.
Zero.
Is 0, no? Because sine hyperbolic 0 is 0. What does it mean? Physically, what does it mean?
No
No
magnetization.
magnetization.
So no net magnetization, no? This is for finite beta. This is fine, no? You have assumed that this is beta is finite, no?
Yes.
That you have, so no net magnetization. What does it mean? In can I say something else? This is actually called no spontaneous magnetization. Why spontaneous? Because your, so not J, your B is 0. In the absence of magnetic field, if I calculate the average magnetization for any finite value of beta at any finite temperature, then the average magnetization is 0, which basically means there is no spontaneous magnetization, okay, at finite temperature. Because you assume that beta is finite, no? Beta is inverse of temperature. Beta is 1 over kBt. So it also means no, if you don't understand, you ask me. Ferromagnetic phase for Ising model in one dimension. So this statement is clear, the one I have written here. What do you mean by ferromagnet? Ferromagnet? What is a ferromagnet?
The spins would align either upward or
So
down.
either all the spins are up or all the spins are down. So what will be the net magnetization for ferromagnet? Sorry, average magnetization for ferromagnet.
Magnetic moment of one spin.
No. If I go to a true ferromagnetic system, then what will be the average magnetization value? Hmm? All the spins are up, all the spins are
Mu,
down. What should be the value?
mu,
Yes. It should be n times mu. You
Plus,
understand?
average will be mu.
Yes. No, no. Average will be n times mu. Mu is for each site now. How many sites are there? N sites. So n times mu.
Ah, sir. Yes, yes. Average magnetization is zero.
If I ask you what is per site, then that is mu. Okay. So all the spins are up, all the spins are down. Now, if all the spins are up, mu is positive convention. If all the spins are down, mu is negative. Okay. Is this clear?
Yes, sir. Yes, sir.
Okay. So, but it is not happening. Is it happening? No.
No.
Your average magnetization is 0, not equals to mu at any finite temperature. But if I keep on cooling that system, what will happen? So what should I do? Actually, I can plot this divided by, if you want, divided by n versus beta. Beta is 1 over kVt. Yeah? How does it going to look like? Any idea? I'll draw it here. What is the average beta small means what? So when beta is small means temperature is very high. At high temperature, what do you expect? What should be the expected value for magnetization? Because spins are completely random, no? This thermal motion that will actually, yeah, that is a good deciding factor. So your magnetization should start from 0, and then actually as you cool down your system,
Completely in mu. Not mu.
yeah, it will go like this, and then it will saturate. What is the saturation value?
Mu.
Mu.
Saturation value is actually mu, isn't it? And if I divide by mu, then it is 1. The way it's got. But this is happening at what? Your average magnetization is mu n, only beta goes to infinity. So Tc is 0. So as if you can go to absolute 0, so if you go to absolute 0, then only you will have a phase transition to a ferromagnetic phase. Is it clear? So this is not a true phase transition. A true phase transition is such that at some finite temperature the change happens. You go from a paramagnetic to a ferromagnetic phase. What is paramagnetic phase? What will be the value of magnetization? Sorry, average magnetization for a paramagnetic phase?
Zero in the absence of magnetic field.
Paramagnetic. 0 in the absence of magnetic field. So you go from paramagnetic to ferromagnetic only when you go to absolute 0. This is absolute 0, isn't it? So that's why I'm saying that in one-dimensional Ising model, there is no phase transition at finite temperature. That's why there is a phase transition at 0 temperature, but people don't call it phase transition. Okay, so people call it that in 1D there is no phase transition. Is this clear?
Yes, sir.
You can see from the expression itself. You can see from the expression itself. Okay.
Yes.
Now I can do one more thing. This is my expression for average magnetization. Now, what I'm doing, I'm just putting J equals to 0. What does it mean if I put J equal to 0?
Non-interacting.
Non-interactive. Spins don't interact with each other. Okay, but B is not equal to 0. So you have some external magnetic field. There is an external magnetic field. Okay, so what is the expression for this? What is the expression? Tell me. B is 0 means this is nothing
Sine
but your
beta b by cos hyperbolic.
what is this? This is fine. Sine hyperbolic by cos hyperbolic, isn't it? Because
1 plus sine hyperbolic square is cos hyperbolic square.
sorry, let me write it properly. I'm giving you all the notes so that when you go and read, you can see everything. Okay, and sine by cos is tan hyperbolic also, isn't it? This is fine. So basically, your
Yes.
this is fine. This is how it is. So actually, we can see this J. This is the coupling, no? What does it do? Uh, it actually leads to aligned phase, isn't it? So higher the value of J, I should go more towards ferromagnetic space, phase rather. And KBT is thermal energy, no? What does it do? Disorder, no? Because it will try to make the system more like uh, magnetization 0, which is basically like a paramagnetic system, isn't it? That is what one should do. If you increase the temperature, it maximizes the entropy.
Yes, sir.
Kinetic energy increase.
Mm. There is no kinetic energy in this case. Okay, the system does not have real kinetic energy because we have a spin system. Okay, so it is completely disordered state. As you increase the temperature and as you increase the J, it should go to ferromagnetic phase. But you see that this never wins in 1D. So that's why there is no phase transition. Even if you make your J very, very high, large, even with that, you'll never get a ferromagnetic phase. Is this clear? With 1D Ising model. With 1D Ising model. Is this clear?
Yes, sir.
Now, what will be the value of this quantity? I have already put B equals to J equal to 0. Now I put B equal to 0. What does it mean? J 0 and B 0. Basically means non-interacting spins and no external magnetic field, isn't it? What do you
Everything
expect?
equal to 0.
No magnetization.
What do you expect?
Magnetization 0.
Are you sure? What is the expression? So let us plot it. Let us plot this expression thing, and we'll see what happens. So this is your expression for magnetization, isn't it? So what is one check? One check is, you see this expression, if you see carefully, that it is what do you call, say, I should not write it here. Okay, I'll not write. I'll show you in the. So if I take it, if I calculate its value, some arbitrary value, at some magnetic field, some say B, and then I calculate the value at magnetic field minus B. So B is equal to -2 and B equal to +2. What do you expect? The values. Values, what do you expect?
Same magnitude, opposite sign.
But same magnitude, opposite sign. What does it mean? So actually, in one case, the magnetic field is like directed in this direction. The other case, the magnetic field is in the opposite direction, isn't it?
Yes, sir.
Depending on the direction of the magnetic field, you will have magnetization. So what do? You just actually plot this quantity from minus B to plus B, or any minus value to another plus value. So it will go like this. This is the plot. Can you see the plot?
Yes, sir.
So this is symmet. This is in term. It is anti-symmetric rather. So what I'm saying that, okay, the magnitudes are same if I go to negative B value, but the sign just reverses. Is it clear? The magnetization sign reverses. But at some point it is 0. When it is 0? When it is 0, magnetization? I have told you already, na? When is magnetization 0?
Zero magnetic field.
External field 0.
When there is no external magnetic field, magnetization is 0. But any finite magnetic field, whether plus or minus, magnetization is non-zero. But there is symmetry in the expression. So this is one way to check that your calculation is correct, because plus B and minus B should give you the same value of magnetization, only the sign should be reversed. Is it clear? It has to be. There is symmetry in the problem itself. So now you can plot this at different values of, say, coupling strength J. J1, J.1, J.3, and J0. And now if I plot them together, this is a plot. Can you see the plot?
Yes, sir.
This one. Now can you tell me, you can see the color, no? Purple, blue, and red. Which one is for higher J, which one is for lower J? Can one tell me? Which one is for higher J, which one is for lower J?
Blue one is for higher J.
For higher J.
Why blue one is for higher J?
Sir, because J is causing average magnetization to increase by decreasing the fluctuations by antagonistic play.
Yes.
So that means more the J, more is the average magnetization.
Very good. Very good. So actually this pink, or not the pink, yeah, it's a pink. Pink curve corresponds to J0. There is no coupling between the spins, the pink one. And as I increase the J, it becomes stiffer, isn't it? Becomes stiffer. Okay. And is there any other way to make this thing stiffer? Extremely stiff.
By decreasing the temperature.
By decreasing the temperature. So what should I do? By decreasing the temperature means what will be the value of beta? So again, I go back to the expression you see here. Even here, if I take in the limit beta goes to infinity, what will happen to the magnetization? What is the value? Tell me. Beta goes to infinity. That is what you want, no? Very large beta. Sorry, where is that? Yeah. Very large beta. What do you expect? Very
It
large beta?
reaches it reaches to its highest value mu.
Yeah. Show me how. Show me how.
The exponential term vanishes and the
Then
sin
what?
h numerator cancels with the square root of sin h square in the denominator.
Yeah, yeah. So you got it, no? Essentially, it is n mu. Sorry for this handwriting. You have sine hyperbolic. B beta is there. And then here, very easy actually. This time is equal to 0, no? Because is 0, no? Exponential minus infinity is 0.
Yes, sir.
So this will give you n mu. So this is, see, this is independent of B, isn't it? For any finite B. For any finite B, this is fine. Okay. So what do you expect? So yeah. So if I actually make a plot of this magnetization at very high value of beta or low temperature, going to absolute zero, I should get very steep, like a step function here. Step function and also another step function in the negative direction. This is expected. This is what you expect when your temperature is low. Your temperature is low. Look at carefully
Yes.
and see. This is for any value of B, isn't it?
Yes.
So it doesn't matter what magnetic field you apply. It doesn't matter what magnetic field you apply, isn't it? What happens when I go to absolute zero?
Zero magnetic fields.
So basically, your magnetization becomes plus minus n mu, rather two values. So now let us show you the plot of this. I have just created an animation, and you can see that. So this is your magnetization as a function of magnetic field. Magnetization is a function of magnetic field. So as I increase magnetic field, what do you expect? Not magnetic field, as I increase, sorry, the coupling strength, what do you expect?
Steeper.
Steeper.
So let us see. It's becoming steeper, no? After a while, you cannot see actually, it becomes so steep. Can you see? So now I am going the other direction. I am just making the value of J smaller and smaller. See. Okay. And also I had showed you that if I and if I have zero magnetic field, what is the magnetization? I asked that question, no? What is the magnetization? Zero magnetic field. Look at this expression. Why? Why zero?
Because at finite temperature, sin hyperbolic beta B will be zero. If B is zero.
Are you sure it is zero? No, I'm just asking. Maybe you're right.
First, you had asked B zero, right? B is equal to zero.
Maybe zero.
Then at finite temperature is magnetization will be zero.
So when B is zero, look at this expression. it is sine hyperbolic 0, which is equal to 0. For temperature is finite. Okay, at finite temperature, magnetization is 0. Is this clear? 0 when J is 0. I am saying J is 0. Okay, is this
Yes.
clear? Is this clear? Is this clear? So basically, I can plot this quantity also, that the magnetization when your spins do not interact. What is the expression? This is n mu tan hyperbolic, isn't it? Beta B.
Yes, sir.
So let us plot that. So your what is that? In this case, where your J is 0. Is the expression, no? This expression, just you can simplify it actually. I don't know whether it will do. Try. Okay. It doesn't do any anyway. Okay, doesn't matter. This is a tan hyperbolic. You can see this, no? This is tan hyperbolic. So now if I plot this plot, if I plot this quantity, for example, as a function of because there is nothing called J here. Sorry. Okay. So beta some finite temperature. It will look like, it will be like this. Is this clear? That magnetization, this is for a ferromagnetic, sorry, for a paramagnetic system, isn't it? Sorry. And like what I'm saying, that it is not a paramagnetic system, I should not call it. I should call it, this is for a system where the spins don't interact with each other. There's no J, only a magnetic field, applied magnetic field. So there is, when there is no magnetic field, your magnetization has to be what? 0, because they're randomly oriented. As you apply the magnetic field, the spin start orienting itself, aligning with the magnetic field. That is the tendency, isn't it? And eventually, when your magnetic field is very, very large, then only it becomes equal to, you understand? Then only it is, when magnetization becomes +1 or -1, or plus n mu, plus mu or minus mu per side. Is this clear? Hope we are following.
Yes, sir.
Now, if I make this plot at 2 different temperatures, what do you expect? This is at temperatures at 30 degree, and then I do 30. Say I do at 300 Kelvin and then 350 Kelvin. What is the expectation? Physically, think.
Curve should become steeper.
What others think?
We reduce the
Yeah, sir.
temperature.
In the lower temperature, it would be steeper. Curve would be steeper.
Lower temperature. Lower temperature means higher value of beta, and you expect this curve to be steeper. Yes, you're right. It is steeper. If I don't need to go. Now, why it is show?
So because temperature is trying to like it is like fluctuation, it is trying to disorder the system.
Yes. So
And
that's yeah. Complete your statement. Yes.
the more the temperature, the more the strength of
Strength
the
of
disordering.
increase.
So that's why it is more curvilinear in that sense.
Basically, I take a system where there is no coupling between the spins, but these spins are sitting on a side. They don't interact with each other. I have an external magnetic field, and I do experiment at two different temperature, at low temperature and at high temperature. Okay, low temperature and high temperature. And what do you expect at high temperature? You are saying that high temperature, my expectation would be what? My magnetization should be
Lesser as compared to lower
lesser.
temperature.
Why?
So
Why?
because it is disordering, the temperature is like it is a thermal fluctuation. It is trying to disorder the system.
So basically, you have to freeze your system. You have to cool down your system in order to get make magnetization non-zero, isn't it? So it will be steeper as you cool down your system, as you decrease your temperature, decrease the temperature of the system, isn't it?
Yes, sir.
Your magnetization will be. So you have to go to a lower temperature, lower and lower temperature. Then only it will go show you a magnetization, net magnetization,
Sir,
which
hello,
is
sir. Sir, why don't we call it a phase change phenomena here? Because we can see two phases.
no, it is not phase change because it is not happening at the finite temperature. So if this is not happening at finite temperature, if you go to absolute zero, you can have it.
Okay, so it is like a pseudo phase change
Yeah,
phenomena.
it's not a true phase transition. True phase
Mm.
transition means there will be a sudden change in magnetization at a particular value of um, sudden change in magnetization at a particular temperature, which is finite, not absolute zero. So if you have a change in magnetization, sudden change at a temperature which is not absolute zero, then I would call the phase, the system to have a phase transition, true phase transition. So, but one-dimensional Ising model do not show any phase transition. Is this clear to
Yes, sir.
all of you? Because at absolute zero, you don't see any phase transition. Okay? Is this clear to all of you?
Yes, sir.
Yeah. Now the point is that although 1D Ising model does not show phase transition, it is a very useful model because this is analytically solvable, and people make use of this model in many contexts, many types, model building and other contexts, physicists, chemists also. Okay, so that is very useful. I think everybody should know, whoever is taking statistical mechanics course. Now next step is two-dimensional Ising model, and this is extremely difficult to solve, and it was solved, I think in the last class, it was solved by Ongzagar. It was solved by Ongzagar in much later. Ongzagar solved it 1944, 2D Ising model. And this, and also there are people who later solved it with the magnetic field. This is B0, and also people solved it by non equal to 0. And the best thing about this 2D Ising model is his name is Lars Ongzagar. I think he's the finest theoretical chemist, I would call it. And Ongzagar got Nobel Prize in chemistry. How many of you know that? Do you know why? In which area of chemistry he got Ongzagar Nobel Prize in chemistry? Go and check. There's something called Ongzagar regression hypothesis. Because of that, okay, linear response. This is a non-equilibrium statistical mechanics, not for Ising model anyway. So, but the best thing about this 2D Ising model, 2D Ising model means what? You have a lattice, no? And you have spin sitting there. Could be up, down, up, down. This is a very tough problem to solve. Okay, and this is solved by Ongzagar, and later people also, there are other people who also did this. This can be solved. This is solved analytically. This can be solved on a computer, but Ongzagar solved it analytically. It's an extremely tough problem. And it shows what is known as you expect, it shows a phase transition. Although one-dimensional Ising model do not show phase transition, but two-dimensional Ising model shows a phase transition, which basically means transition to a ferromagnetic phase at finite temperature. Is this clear? Now, can anyone tell me what do you expect if I plot magnetization as a function of, say, temperature? How does it going to look like in this case?
There is a
actual,
phase transition in the
yeah.
graph.
So actually, if you and I plot this average magnetization as a function of not beta. Beta was inverse temperature. I had plotted as a function of. We had this plot. I can plot also as a function of beta, but say let us plot as a function of temperature. What is the expectation in 1D Ising model? When temperature is 0, what is the magnetization? What is the magnetization? When temperature is 0, what is the magnetization?
N mu.
N mu.
Yeah. So average magnetization is something like n mu, whatever. So divided by n mu. So what is the value? 1.
Unit, yes.
1. Okay. And 1. Is this fine? Is this fine?
Yes, sir.
And what is the other expectation? And this magnetization will be 0 what time at what temperature?
Infinity.
Only here. This is like 1D Ising model. This is asymptotical, only in the infinite. When t goes to infinity, your m goes to 0, isn't it? It's clear. But what have people seen in experiments? Okay. And with this model, actually, rather with this model, 2D Ising model. 2D Ising model, what do you expect? Maybe it will go like this. But you understand, this is a critical temperature. Is this clear, Anish?
Yes, sir.
Sorry. I hope I have not done anything wrong. So basically your TC actually this curve is not correct. I'll tell you. 2D Ising model is fine. But in 1D Ising model, what I had here, I had this. If I plot as a function of beta, what is the plot? What is the plot for angulation? It is like this.
0 beta.
0 to
So if I now let us go and plot it as a function of 1 over beta. Let us do it. Just to get this is how it is expression. So now Plot this. Um, for some reason. So it will be something like this if I plot, isn't it? If I plot this magnetization, so it is at very low temperature, magnetization is 1, and then it drops and goes like this. So it will be like this. I think this plot is fine, no, Anish? I'm just thinking.
Correct. I mean, if you consider a temperature less than Tc,
Yes.
the 1D Ising magnetization should in principle be lesser, right?
Yeah.
Than the 2D Ising, because the 2D Ising is in the ferromagnetic phase.
Yeah. So basically, I think I should not plot this. Better is I don't plot it here. That's a better thing to do. This is 1D Ising, no?
Yes, against beta.
This is 1D Ising. So basically, in 1D Ising, this transition will happen. This see, this transition will happen. Actually, happens at very large value of beta, which basically means when temperature goes to 0. For 2D Ising model, it will happen at finite temperature, isn't it? You don't need to go to 0 temperature. It will happen here. But 1D Ising model, I think you have to go to very, very, very low temperature in order to get this, isn't it? So it will be something like this, no? Like this. If I plot, Anish, if I plot the 1D Ising model here, okay, average magnetization divided by temperature. So your average magnetization becomes 1 when? At absolute 0. And that
Yes.
happens asymptotically, isn't it?
Yes.
So basically, at any finite, if you go to any finite value of beta, your magnetization is below. It's not 1. It's less than 1. So maybe 1D Ising model will be something like this. Can you see? Like this.
Yes, sir.
Maybe I'm saying because I like it should be something. Strictly speaking, it will be like this line goes like this, and only when you hit temperature goes to 0, it will become 1, isn't it? In magnetization. You understand what I'm saying? At high temperature, what is the magnetization? For Ising model, 0. 1D Ising model. Anish, another. For
Yes,
1D
sir.
Ising model, let me write down. Okay. When temperature is, say, large, greater than 0, what is the value of magnetization? Tell me.
Less than
Less
1.
than 1.
Less than NU. 0 for very large temperature.
Basically 0 if it's a very
Yeah.
large temperature. So large temperature is 0, so it will go like this, and actually it will only it becomes 1 when your temperature becomes 0. Okay, what I'm saying. But in
Yes.
2D Ising model, it will happen much earlier at much higher temperature. I'm just going down in temperature. You understand?
Yes, sir.
But it is very difficult to like draw it together. I don't know how to draw it here because
So
the
it would
scale
be,
will
I
be
guess,
very difficult
lower.
because it will go like this, and then suddenly at some temperature it will increase, and then it will become 1 at 0 temperature. Okay, but this has become 1 at much higher temperature, higher than 0. Critical temperature is greater than 0 at finite temperature. Yeah, any question?
So, sir, essentially in 1D, it would be always lower than the
Yeah,
2D.
I think
Mhm.
yeah, not I think, I'm sure, but I don't want to draw it here because it is not correct to draw them together, these two different systems. Okay, so we'll stop here today because I wanted to start something different, but I don't think I have time enough time, because if I start today, uh, what is going to happen that I'll not be able to finish. It is better to start with a new topic in the next class. So next class is on Monday. Next class is on Monday. Okay.
Yes, sir.
So Monday we'll start with the liquid state. So I hope you have followed Ising model because this is very important. I hope you have.
Yes, sir.
Yes, sir.
And please read this from the book by Patria. Okay, Patria, I told, I think already. No, did I tell you the book?
Yes, sir. In quantum statistics.
Yeah. So R.K. Patria or Professor Biman Bakchi's book, both the books are good. Read. Okay, there could be typos in one of the books, so little careful with the typos. So now we have some idea about phase transition, isn't it? B condensation and phase transition. Again, that critical temperature is non-zero, low temperature but not zero temperature, isn't it? In 1D Ising model, no phase transition. In 2D Ising model, I told you there is a phase transition. Actually, what happens in 2D Ising model, this spin interacts with this and this and this. You have many neighbors for a spin, depending on the lattice you choose. And as a result, it can go to what is known as ferromagnetic phase. But in 1D, you don't have enough number of neighbors for a particular spin, and it will never go to ferromagnetic phase by phase. It will never go to ferromagnetic phase in 1D. So that at finite temperature. Only when you cool it to zero temperature, it will go. This is very important that 1D Ising model do not show any phase transition. Is this clear? This is very important. But 2D Ising model shows. So 2D Ising model is an example which shows phase transition. Okay, so with that, I'll stop today. And thank you very much for your attention. And we'll meet on Monday.